Hello and welcome to the WeLEAP Enlightening Talk series. Today we have Dr. Cristina Riso. She is an assistant professor in the School of Aerospace Engineering in Georgia Institute of Technology. And this is the continuation of our conversation with Dr. Riso. Those of you who joined us in part 2 directly, please check out the part 1 where we discussed more about Dr. Riso's experience during the undergrad and in her early career, how she prepared for her faculty job and other related things. So now in this part of conversation, we will focus more on the research projects ongoing in her lab, and we will learn more about her experience as a faculty member at Georgia Tech and lots of tips and suggestions for new faculty members in different universities and how they can thrive in those circumstances. We will also have some questions related to the application processes during the PhD or postdoc program, and also any helpful information for women in aspiring for long-term research career. So stay tuned. So with that, Cristina, welcome back. Thank you for staying with us for this longer conversation. So with that, I will just ask you to share a little bit about your projects, recent projects, or maybe future projects which you're working on.
Sure, let me just share my screen. All right, so yes, I will give you an overview of my research, and then I will dive into one of the projects that I'm currently working on. So to give you some background, my work is in the field of aeroelasticity that looks at interactions between inertial, elastic, and aerodynamic forces, for example, on aerospace vehicles and components of these vehicles, such as wings. And the goal of my research is to really enable future aerospace vehicles by addressing some of the challenges that these vehicles that these vehicles pose in the field of aeroelasticity, which is where I specialized. So if we look at, for example, the examples of future vehicles that are being considered or are under development for the future, these are quite different from the aerospace vehicles that have been developed so far. And there are many challenges when we look at aeroelasticity as a discipline. The ones that I focus on are these three that you can see here. So first, it is impossible to look at aeroelasticity as a standalone discipline. So we need to really take into account interactions between aeroelasticity with other fields that are typically studied in a separate way. For example, flight dynamics, controls, or thermal effects, propulsion, all has to be considered together because these configurations have close interactions between these different fields and disciplines of aerospace. For example, you can think about configurations that have tightly integrated propulsion systems with the airframe, or for example, configurations for a high-speed flight where thermal effects play a role, or configurations with very long and slender wings that are very flexible, that have all kinds of mutual interactions between rigid body dynamics, rigid body motion of the aircraft as a whole, and aeroelasticity that looks at flexibility and structural response under aerodynamic loads. So this is one aspect that I focus on. Then typically most of aeroelastic problems to date, especially from a design perspective, have been tackled using linear models. And by linear, I mean models that assume either typically both linear structural dynamics, so very relatively small deflections in the airframe, and also linear aerodynamics, for example, lack of effects such as transonic effects or stall effects that are important for some of the next of the configurations that will be developed in the future. So there is a need to get to develop well-established nonlinear models for aeroelastic problems, and and also to make them computationally efficient and robust enough so that they can be applied for design studies, because the scalability is also a key problem that has to be addressed when we want to use new models and new techniques to really design future vehicles. And finally, another problem is that these configurations are very unconventional in the sense that they are different from the ones that we have a lot of experience from a design perspective. So it is important to establish knowledge and design guidelines and computational tools that can support the design to avoid having to test and do experimental studies of these configurations where we have to learn everything about the way they behave. So I look at these problems from the perspective of modeling, analysis, and design, and these are three areas where my research is currently focusing on. From a modeling perspective, I specialize in the aeroelastic modeling of future aircraft. So I've been mainly focusing on high aspect ratio wing transport aircraft, such as, for example, these configurations that you can see here, or these configurations that you can see in this figure here. I'm also starting to work more in the area of vertical lift and urban air mobility, for example, looking at other types of configurations that have vertical takeoff landing capabilities, or that can be used for regional and urban air mobility. And my goal is to develop computational models that can be used to study these configurations from an aeroelastic point of view, taking into account interactions with other disciplines, and focusing on developing so-called low-order models, meaning that I'm not as interested in developing high-fidelity computational tools and very expensive calculations, but I'm more interested in developing models that are as simple as possible while still capturing the key physics that is important, for example, from design space exploration perspective, or from a sensitivity analysis perspective, so that we can use these models as tools to explore the behavior of these vehicles and understand how to design and how to operate them in the future. I also focus on, once we can model these configurations, I focus on analyzing their behaviors, and especially one area that I'm very interested in is the prediction of dynamic instabilities in aeroelastic systems that are, for example, such as, for example, flutter and the corresponding dynamic responses once for example, a wing becomes unstable and starts to vibrate. I've been mainly focusing in very flexible wings, and recently started focusing on whir flutter, which is a type of instability in wing propeller systems. As you can see, for example, this kind of configurations. But in the future, I'm also interested in exploring other types of instabilities, how to characterize them, how to prevent them, and how to understand how to design these vehicles in a way that these instabilities don't occur, or they occur at flight conditions that are not of interest from a certification perspective, for example. And to do that, I've been working in the area started working in the area of design optimization during my postdoc, trying to develop formulations to bring aeroelasticity considerations and dynamic aeroelasticity considerations, especially in design optimization, to put them as constraints. So we wanted to design more efficient, for example, more energy efficient vehicles for better lower environmental impact, but we also want to put some constraints on the aeroelastic behaviors, so that, for example, we don't develop vibrations and oscillations that can destroy the structure or can be undesirable for performance and for safety. So I will talk a little further on these two topics that are related to each other. So on one side, being able to predict these dynamic instabilities, and on the other hand, be able to do that in a way that we can use these predictions for design. So just to give some motivator for why we are interested in this type of predictions, so we know that when we move from this kind of wing design that is representative of, for example, a wing that is flying today, of an aircraft that is flying today, to a future design with a longer wingspan for higher energy efficiency. On one side, we have an improvement in, for example, fuel burn, but we also have lower structural stiffness that brings higher flexibility. When this happens, we have a variety of problems. One problem is that if we look at the damping of the wing, for example, when it responds to vibrations, to disturbances at different speeds, we have a decrease in damping for a certain flight condition, which means that the onset of instability is anticipated. So we have more unstable wings that can develop diverging oscillations more easily at conditions that would otherwise be stable for more conventional wings. So one way we can address this problem is that we can design these new wings through a design optimization process, and we can put flutter, which is the onset of instability that is denoted, for example, by positive damping, which translates to a diverging oscillation, as a constraint, in a way that we develop a wing that is not only efficient, but also safe from a dynamic stability perspective. The other problem is that if we look at what happens in terms of dynamic response, we may observe a situation like this. These are called the bifurcation diagrams, and they show what is the steady state oscillation that, for example, an aeroelastic system such as a wing develops under a disturbance at a certain flight condition, for example, speed. So for conventional wings, we typically, if we have the instability that occurs at this point, we can have oscillations of a certain amplitude only after that point, which means that if we fly conditions before where we know the stability is going to happen, we are safe. We are not going to have self-sustained oscillations that stay there with a constant amplitude in time that can damage or destroy the structure. If we go to more flexible wings, however, not only we have the instability that may happen, for example, at a lower speed, but we also have this situation where even before the instability occurs, that corresponds to where we have positive damping from a linear perspective, we can have a bistability region where if we get disturbances beyond, for example, this threshold, after some time, the oscillation will decay. But if we get large disturbances, for example, here, the wing will develop a constant response amplitude, so an oscillation that remains in time. So this is very dangerous because it gives these vibrations that can destroy the structure, damage the structure, and they are dependent on the type of disturbance that one experiences during flight. So there is really an interest also in characterizing these bifurcation diagrams to understand the nonlinear response and possibly avoid this kind of behavior that is called subcritical bifurcation, where we have this bistability by putting constraints also on the dynamic response in optimization. So this is an area I started working during my postdoc, and I'm really excited about because it becomes more and more pressing as we move toward more flexible wings, and it's also a problem that may arise in other systems, such as, for example, wind turbines or helicopter blades, all kinds of systems that can develop aeroelastic instabilities in the presence of nonlinear effects. And just to give an example, this is a wing that is being studied under a working group in the Aeroelastic Prediction Workshop. That is one activity in the Aeroelasticity community I'm part of. So you can see it's a very flexible wing that is deflecting quite a lot. And when we looked at the so-called flutter boundary of this wing, so this solid curve here denotes where our numerical model predicts the onset of instability to be. and the black markers are instability points obtained from wind tunnel tests. So what we can see is that when we start increasing speed at a certain angle of attack, we get an instability which compares relatively well with our numerical prediction based on linearized eigenvalue analysis for the wing. But then when we continue the speed further, the numerical model will tell that at some point the wing gets stable again. And the experimental data say something different, because we have that kind of bistability behavior where for a certain flight condition, depending on what is the level of perturbation that we can have either a stable or an unstable response. So this is just to say that this kind of behaviors exist in real wings, and as wings become more flexible, it is more important to be able to characterize this kind of behaviors and understand what is happening, for example, in this region, why the numerical model based on linearized theories says the wing should be stable, but it actually is not. So the idea is that this kind of behaviors cannot be predicted by traditional tools that are based on linearized analysis. To give some background on that, it's if we consider, for example, a varying speed as the parameter, our linearized analysis would say that at some point we have a speed where beyond that we have an instability that grows. So for a traditional linear system, if we look at the response, for example, of a wing point, we excite the wing and we look at how the displacement of that point varies over time. Before the instability point, we would see a converging oscillation. And beyond the instability point, we would see an oscillation that in theory goes up to infinity, because it's dynamically unstable. If we have some nonlinearities of the right type, beneficial type, we can have a situation like this where before the instability point, we still have convergence toward some equilibrium state. Beyond the instability point, instead of growing to infinity, at some level of amplitude, the nonlinearities play a good role, and they stabilize the growth of the response of the system in a way that the system develops a constant amplitude oscillation, which is better than diverging completely, but is still undesirable because we can have, for example, degradation of performance or damage, fatigue, and so on. And then there are other types of nonlinearities that trigger these subcritical behaviors that I talked about before, where there is this bistability region where before this point there is a convergent response. After this point, there is a diverging response at the beginning, but then there is a constant amplitude oscillation that develops. And then there is these unstable points, bistable points, where depending on the level of perturbation, we can either have an oscillation or we can have a decay toward equilibrium. So the bottom line of these graphs is that if we look at how the response of the system varies with a parameter, for example, speed before the instability, we can see that, for example, in this case here, we have a very fast recovery. It takes just this time for the system to recover to equilibrium. But if we move closer to where the stability happens, we see that recovering to zero response takes much longer. So these signals that we can extract from an aeroelastic system before the bifurcation, before the flutter occurs, the instability occurs, tell us something about how the system is going to behave after the instability has occurred. So I've been working on techniques that essentially look at how the envelope of the response varies with amplitude and also with a parameter, which could be speed or a design parameter, to try and understand how we can predict this kind of response beyond the instability occurs, but only looking at the behavior of the system before, so that we don't have to study, for example, or simulate this kind of oscillations, but we can study the behavior from before the instability occurs and gain some insights into the behavior beyond the instability. So this idea to look at how transient responses vary with amplitude and with the parameter was developed by a research group in the Department of Mechanical Engineering at Michigan. This is one of the first papers that came out from that work. And starting from there, in the past few years, I've been working mainly on this methodology from an aeroelastic point of view. So leveraging a tool that is general can be applied also to other types of systems, especially to study aeroelastic instabilities in wings, very flexible wings, and I hope to expand this kind of approach further to study other types of instabilities in, for example, transonic wings or wing propeller systems and other types of systems that develop this kind of problems. So just to give an idea of how it works, we basically look at the slope of the envelope of the response at different amplitudes during a decay, and also different values of a control parameter, for example, speed or other parameters as well. If we compare a fixed amplitude, the slope at a fixed amplitude and for different values of a control parameter, we can see that as we approach the parameter value where we have the instability, the slope decreases. So if we can predict the slope and then extrapolate to get where the slope is going to be 0, we can anticipate where is the point, a point on the bifurcation diagram, which is this graphical representation of the oscillation amplitude versus parameter that we can draw to study the behavior of the system once the instability has occurred. So there was a previous formulation that was considering one parameter at a time, for example, only speed as parameter or only another parameter separately. And I developed a formulation that can account multiple parameters simultaneously, especially to expand this idea of looking at the slope and then extrapolating the slope to get the bifurcation diagram with respect to an arbitrary number of parameters, because this is something that is very interesting, for example, from a sensitivity analysis perspective or a design study perspective, where we want to vary both flight condition parameters such as speed, density, angle of attack, and so on, but also design parameters, for example, stiffness or wing shape and other kind of design parameters that we want to study. So in this paper here, we developed the theoretical formulation, and we did the first demonstration for an analytical system where our predicted points on the bifurcation diagram matched the prediction that you can see in the surface, which is the analytical solution for this simple analytical equation that has that kind of instability. And more recently, we also worked on a very flexible wing test case where we use the time histories from, for example, strain measurements at a point of the wing, which can mimic something that we can do, for example, using experimental data. And using only 3 transient simulations, we were able to predict this whole bifurcation surface, which would have taken much more time to compute, for example, doing a direct time matching approach where we simulate the response of the wing for each flight condition, each design parameter, and we wait for an oscillation to establish to get the amplitude. So we were able to get a 2-parameter case, and I'm currently looking into expanding this further to scale to more parameters and do more extensive design studies to basically understand these behaviors and understand how to design aeroelastic systems to shape these curves in the way that we want. So just to close, some other work that is still related to this topic that I'm working on is other approaches to predict this kind of bifurcation diagrams. I recently we recently published another paper where we try to do these predictions in a different way, using some evaluations of the nonlinear function of that describes the mathematical model without doing transient simulations, which gives some approximation of the true solution that you can see here, but in a shorter computational time. I've been working on plugging these analysis tools into optimization so that we can optimize, for example, a bifurcation diagram of an aeroelastic system to change the shape and get, for example, a lower amplitude of the response at a given speed, and studying these bifurcation diagrams for different wing test cases to understand what amplitude range, for example, the wing experiences during oscillations, and how it varies with different, for example, angles of attack or speed values to understand the nonlinear dynamic behaviors of these wings. So this is one of the areas that I'm working on, and it fits into the overall picture of developing models and analysis methods to study aeroelastic problems, so looking at interaction of inertial forces, elastic forces, and aerodynamics in new aircraft designs that have new aeroelastic challenges that we have to take into account.
Mhm. Wow, thank you so much. It's an interesting and also very challenging research problem you are working on. So thank you for sharing that. And also, as the aerospace industry is moving more towards the zero emission aircraft, given the climate change challenges, it's extremely important to come up with novel aircraft architectures, and we saw some of those novel architectures in your presentation also. I think most of those aircraft were either like high aspect ratio wing or a blended wing body or distributed propulsion system. So yeah, and then the modeling of aeroelasticity and prediction of stability becomes really important. So that's nice. And then of course, like having a large aspect ratio wing is one way to make a highly efficient aircraft design. And the beauty of your work is also in, I think one of the beauties is in developing the low order models, which have a lower computational cost, specifically in the conceptual design stage. So that's wonderful. Thank you. So,
Thank you.
just to summarize in simple words, like what would you say is like, or one or two main challenges in predicting that subcritical bistable zone?
It's the fact that there are some techniques are very robust, but they're not computationally efficient. Other techniques are more computationally efficient, but they are not robust, or at least robustness and the scalability has not been assessed. So I think it's one of the main challenges is that one aspect is to do one analysis for an academic test case and for one setting that we want to try. So I mean, a lot of methods may work in that setting in order to give a prediction, because we can tune all the parameters, we can spend maybe a lot of time perfecting the results. But the real challenge is that if we want to study these behaviors from a design point of view, and we want to take these things, we really want to have this kind of configurations that have all these aeroelasticity challenges, such as the subcritical behavior. We need to think of methodologies that are scalable, or even if they are not scalable, we need to go and try and see how we can scale them, or how we can modify them to be able to tackle both the complexity of the configurations that we want to design, because one thing is to study a simplified test case that is good for understanding of the phenomenon, but is not directly what actually needs to be built and flown. And the other issue is the time. So even if the configuration is simple, having large computational times and a lot of user in the loop solutions is good when we have we can spend time to focus on getting very good result by refining and refining and refining. But if we want to study a variety of parameters, variety of load cases and test and flight conditions, which is what is important from a design perspective, we need the methodologies that are scalable and also robust. So they don't need a lot of knowledge from a user to know how to vary all the parameters, all the settings that can play a role in the methodology to be able to get a good prediction in a short time. So those are challenges not only in the frame of predicting subcritical flutter, but also in general in nonlinear aeroelasticity, because when we move from linear models where there are very established computational tools, both on the modeling side and also algorithms to solve problems. When we start to enter to insert any source of nonlinearity and potentially combine different sources of nonlinearities together, modeling becomes more difficult, analysis becomes longer, less robust, and it requires more knowledge, for example, of how to avoid the numerical issues, how to make the solution converge. And that requires a lot of user experience and time that prevents, in my view, really going to a wide use of these tools because, for example, from an industrial design point of view, it's a tool has to deliver a good result in a short time. So the combination of the result being good and the time being short to get that result is a real challenge in broadly in nonlinear aeroelasticity and specifically in flutter and subcritical bifurcation prediction, which is one of the areas that I focus on.
Yeah, that's great. So one more question I had is, so in terms of model development, do you mainly rely on CFD and experimental data, or are you also utilizing machine learning techniques or planning to utilize them in future?
So I haven't looked into machine learning so far. It's something that I would like to explore at some point. For now, I mainly use high fidelity computational tools such as high fidelity. I'm more on the structure side, so I don't do as much CFD, but I collaborate with people that do, or with people that do experiments. So try to get those data and integrate them in a simpler model. For example, using high fidelity data from CFD to correct, for example, an analytical model or a simpler model that can be used to do quick studies on a variety of, with a variety of different parameters to explore the behaviors, but still retaining some information from those more detailed modeling and analysis tools that are available today, and as well as experiments that can also enhance lower order models, bringing data from actual wind tunnel tests or flight tests. And all these modeling techniques, in my view, they don't fight with each other because they serve a different purpose. So low order models cannot replace CFD. CFD cannot replace those models in the sense that they are different tools for used for different kinds of studies, different stages of the design, different stages of the understanding of how a system behaves, and they can complement each other in a way if we know how to interact with people that have all these different expertise, and also we know which is the right tool to use at the right time, and not use something that is less sophisticated or more sophisticated than needed to get a particular prediction.
Yeah, okay. And you talked about the challenges in predicting the aeroelastic behavior for a large aspect ratio wing. But I noticed in your pictures, it was mostly like the wing isolated from the propulsor. So for example, in a distributed propulsion framework, or even like the conventional propulsion, but with a very large aspect ratio wing, it becomes important to see the integrated system. So have you looked into that at all, or are you planning to? And what will be the main challenges there?
Yes, so that's a great question. I'm starting now working on that topic. I have a new project that started when I joined Georgia Tech, looking at basically instabilities in wing propeller systems. And one of the challenges is to account for the aerodynamic interactions, because there is a need for example, if you have a clean high aspect ratio wing, to some extent, a quasi 2D analysis with the corrections for the wingtip effects may still deliver a pretty good result. But if you have a wing that starts to have a very large fan or a bunch of propellers along the wing, then it becomes more and more important to take into account those aerodynamic interactions to predict the overall dynamic response of the system as a whole. So that is something that requires it has challenges on the modeling side, because there is a need to account for these interactions, and also it has challenges on the analysis side, because accounting for those interactions brings more complex models, and models that may take, for example, larger computational times. So it triggers also a need to enhance the analysis methods so that they can be faster given the higher complexity, for example, of the model that is needed to capture those interactions. But that is a very active the study of these wing propeller interactions and wing engine interactions is very active. Is a very active field, because there are a lot of new configurations that have shown that there are benefits from a variety of points of view in considering more integrated wing propulsion systems and different ways to place different number of propellers and different ways to put the propeller on the aircraft to get better performance than with a traditional design. So those behaviors need to be studied, and also we need to build up computational capabilities to be able to do it in a fast way and in an accurate way.
Yeah, and the tools you are building are also like extremely essential for studying advanced propulsor concepts, like such as boundary layer ingestion, where you place the propulsors in a way that some of the flow over the wing or under the wing is ingested by the propulsor, and it makes the whole system more efficient. So yeah, like this aeroelastic prediction with a high confidence, it becomes really important. So thank you for sharing this very exciting and I would say much needed work in aerospace industry. And
Thank you.
all the students listening here, if you are interested to learn more about Dr. Riso's work, you can check out her website and also contact her if you are interested in joining her lab. So thanks again for sharing, Cristina.
Thank
Uh,
you for the opportunity.
yeah, so I'll now move more towards like your current engagements in different technical committees. So, for example, you are an active member in Structural Dynamics Technical Committee under AIAA, and also the Aero-Elastic Prediction Workshop for the Large Deflection Working Group. So, how is that experience? How did you get involved, and what would you suggest to other researchers who are still in like at earlier stages of their career, how to get involved in these and how useful are these activities?
My suggestion would be to approach people who are in those communities, because my experience has been has been always positive. Whenever for example, I wanted to be engaged in the structural dynamics committee, I used to attend the meeting that the committee had at conferences. It's typically SciTech. This was pre-pandemic when I did that. So I asked to join as a guest, because I was interested in learning more about what the committee was doing and what were the different possibilities to get involved. And I always got very positive responses. People are typically looking for younger generations to step in and to contribute. So even though it may feel intimidating to reach out, for example, to senior people in the field, I found always very, very positive responses when I did that. And it always helps if maybe you have a shared connection with someone that can do a smooth introduction. But in general, I would say it's important to leverage all kinds of opportunities to get to know more people in the field, especially if it's a field that one envisions themselves staying for a career. Yeah. The sooner one starts to have the connections, the better, because some fields, like for example my field, they are pretty small worldwide. It's not a lot of people working on that topic. So once you build a connection, those are people that you will always meet in whatever relevant activity your discipline organizes, or whatever event is happening, such as a conference or a workshop or a meeting. They tend to be very always the same people, or almost the same people. So it is of course good from a networking perspective, but it's also good, I would say, from an emotional perspective, because sometimes I feel of my field as my like my second family, in a sense, my professional family. So I really feel that that is a field I belong. I know most of the people by now, because I've been in the same field since my PhD. So I had some time to start meeting people. I don't know everybody for sure, but I know quite a good number of people that, for example, going back to what I was saying regarding not being able to, not being comfortable speaking in public, it makes a huge difference when one goes to a conference the first time and you know nobody in the room, and you are speaking to a bunch of strangers, and when you go to your third or fourth conference and you have developed those connections through, for example, working groups or committees, and you are essentially presenting to the people that you normally talk to, it makes a huge difference also from a confidence perspective. So I would definitely encourage people to just learn about what kind of groups are out there, and sometimes groups have events at conferences, like for example all the technical committees from AIAA have a dedicated networking event at, I think it's SciTech, or maybe also aviation. There is an event which is Meet the Technical Committee, where you can sit at a table of a discipline you are interested in and talk to the people, and maybe go and attend a meeting, or maybe just get some more information about what the committee does. And I also really enjoyed when I started collaborating with the committee, even before I joined as a regular member, helping with, for example, technical tasks, such as, for example, abstract reviews, or even outside of the committee, journal manuscript reviews. I really found it interesting, because it's another way to learn about your field, to shape your field in a sense, because you can make sure that there are good standards and they keep preserved over time, and also knowing about other people that maybe you didn't know about, because you read a paper about a new group that wasn't on your radar. So you can expand your knowledge and just keep learning in a different way than just how, for example, it is more common in a sense by searching the literature, or just not having that connection with people.
Mm-hmm. Yeah, thank you. That's very useful to know. And I am sure like it's a very great advice, because like you can prepare and like get involved in these things as early as possible, rather than waiting to be a professor first and then start. So yeah.
Yeah, and I mean, I think it's also important not to feel like one has to do it all. It's not a checklist. Some things you may be interested in, some things you may not be interested in, or may not have the time.
Right.
So it's there are many ways to get engaged in the field. Participating in a professional society in the activities is one of those ways. So, but there are many different ways, and it's important to just know what ways are possible and find what is the way that one enjoys the most, or maybe a couple of ways that one enjoys the most. Because after, I mean, there is a time constraint for everybody, so we cannot engage in all the activities that we would want to.
Yes,
But for example, in my case, I really like learning more, having that sense of community and learning more about what's going on in my field. So for me, being part of a technical committee was very good for that.
Wow, that's great to hear. So, how is your experience as a new faculty member in Georgia Tech? How was your first semester?
It was good. I mean, it's a big change from before. There are many things to learn. How to do and just get a new sense of how to manage my time, how to manage all the different tasks that I have to take care on. But so far, my experience has been positive in a sense. Like I heard when I was asking about faculty career, I heard from some people that managing a lot of different tasks was the main difficulty, and it is. I mean, there is research, there is teaching, there is service, which is all the other things that we do in our community, and then there is administration things, just learning who does what, especially when you change institution. That is also something that takes time. It can be the administration can be as efficient as one wants, but you still have to understand who is the person who takes care of a specific task. So that takes time, and it is true that it's a challenge. I think in that regard, the postdoc helped me because I had an opportunity to try some aspects of the faculty job on a smaller scale, and with the safety of having a PI that was above me and was the person to take the decision in the end. So I had the opportunity to get some training for that, and it was helpful for me. There are also people who go into a faculty position straight from PhD and still succeed. So I mean, again, there is no single way to be to approach a new career and to develop a career. It all depends on what works for one person. For me, the opportunity to try some aspects out and gain not so much more experience, but definitely more confidence in the fact that I could do it was very important before starting. Even though once you are in the faculty job, the feeling that now you are the person to make the calls, like you are the person to decide what you're going, like how you're going to teach that class, what research are you going to pursue, what research are you not going to pursue, which students you want to work with, which ones maybe they are a better fit for something else, or just all the kind of decisions that you have to take that have an impact on my career, but also the development of my own students. So they are even more important because of that. It's definitely, it's something that sometimes, especially in the first few weeks, I will pause and think, oh my God, now I have to take this decision, and I can ask for advice from different people, but in the end I have to take the decision. Nobody can take it for me. It's really, for me it was the biggest change, just the feeling that now everything is my goal in the end, even though I have mentors, friends, colleagues that can advise me, but in the end I have to choose to shape the path, which is exciting, but is also scary at the same time.
Yeah. So you talked about various aspects of your role as a faculty. If you have to just choose one item in two different categories, like what is the one thing you find the toughest, and then what is the activity which you enjoy the most, what would you say as a faculty?
So it's hard because I feel like, I mean, there are some things that are difficult or may feel intimidating. I don't feel there is one thing that I say, I really cannot do this. Like I really would rather do anything else. I mean, like every job, there are some things that one likes more and some things that are just part of the job. So I think the part that I like the most is definitely interacting with people in research, in teaching, also in service, but that is not as intense as interaction as, for example, teaching a class or supervising a student. But that is something that is it's the best for me. So as a not only as a faculty, but as a researcher in general, I get to work with people who are trying to solve difficult problems, which have all kinds of backgrounds, all kinds of expertise different from mine. And just talking to those people, you get to learn by talking with people all the time. So that is something that I really enjoy. And my discipline allows me to aeroelasticity is a little bit of a mix of structures, rigid body dynamics, aerodynamics. So I feel like I have opportunities to interact with a lot of different people from a lot of different areas. So that is something that I've always enjoyed of my field, and I still enjoy now that I'm a faculty member. And also working with students and thinking maybe even a tiny bit of what this person learns or what this person does. It's maybe a little bit influenced by something that I said or an opportunity that I can provide. That is something that is it's the best feeling that you can contribute to your field, not only with the direct research that, for example, I can still do, writing my code, running my simulations and doing my own developments, but I can also shape the field through educating future people that may join the field. So that is something that I really enjoy. Something that there is nothing that I don't enjoy in terms of tough parts. Teaching was definitely tough for me, and still because of my I'm not so much like a person that was born with this public speaking ability. It got better with time from a research perspective because I've given many presentations, I've been at conferences, so on that side I got more confident. And now, even though I may still feel intimidated when I have to speak in front of a bunch of people, I don't think about that anymore. It's just something that I do, period. I don't bother that much. But when I do it in a different setting, it's like going back to the beginning when I was giving my first presentation, for example. The first class that I taught was this semester because I had some teaching experience before, but it wasn't being the sole instructor of a full class. So that was definitely one day that I felt, oh my God, what I'm going to say? What are these people going to learn? I felt really, it was really intimidating thinking about I'm responsible for the learning of other people. So the way I deliver the material can impact if they like or not like this topic, and if they learn or don't learn this topic. So it, as anything, that also got better with time. At the end of the semester, I was feeling better, but I'm sure it's also a process, and it's something that I heard from other faculty, including other people who were in your talk series. I think it's something that is very, it seems to be common, especially when one doesn't have an experience as a sole instructor before starting a faculty career. There is always going to be one. The one is not going to be perfect and is going to be tough to approach. But I think it's important to aim to do the best job that you can do at that time. It cannot be perfect at the right time, but you can make it better over time. So that is something that I try to repeat myself every time I feel I could do this better. I try to tell myself, yes, I can do this better. Next time I can do a little better. The time after it will be even better. And then over time you became good at that, like if you were trained since you were a kid.
Yeah, exactly right. So I wanted to ask, so how was the experience designing your own course right from the scratch? And do you have any quick tips for new faculty members so that they can accelerate that process?
Yes, so I developed all my materials, but I did have notes from people who taught the class before, and there was also a reference book for the class that I was teaching. So my advice would be look for any opportunities that are out there to get some material and an outline of the class, because knowing, for example, what were the topics at a day level, like a calendar breakdown of the topics per week and per day, helped me a lot. I had that from a previous colleague, a colleague that taught the class before, and just knowing what they covered in a given day helped me a lot, because it helped me understand how much detail I would put into the lecture, because I only had, for example, 2 lectures on a given topic. So I wouldn't put a full book just on that, because then I had to move on. So that is something that was very helpful for me. And even if you don't have a colleague at the same institution, you can ask people in your field, or you can ask your PI, your PhD advisor, or you can look online if there is a course that covers the same topic, for example, in online available material, because having a reference helps a lot, especially timing the content, because you can, once you know a subject, you would easily fill a week just with a tiny topic, but you cannot do that in a class. The other thing that definitely not aiming, trying not to aim for perfection, because you can edit a slide for a lecture 10 minutes or 10 hours is still not going to feel perfect. So at some point one has to decide to end and to give the best shot that you can. And mostly something that I try to do, and I hope it came across, trying to bring a little bit of yourself and your experiences into the topic, because that is really the plus that each person can bring, that is not something that a student would read on the book anyway on their own. So for example, how you, if you describe an algorithm or an assumption, how you applied that in your research, or how you saw that when you did an internship, or where you collaborated with other people. I think it may make it very valuable, and can also show people that those concepts don't live only in a syllabus, they live in the real world, and that's why we are teaching them in class.
Yeah, that's right. I mean, like lots of the time students don't understand what all goes into the designing of a new STEM course, and it's just a lot more than just the course content. It's also about like making it accessible to the diverse student population, and also like accommodating everybody, and being inclusive. So of course a lot of technical details, but lots of other skills are also required to have a successful STEM course. So I hope students listening to this conversation can get a sense of that your instructors work really hard to design these courses. So hope you appreciate that. And actually at MIT Teaching Plus Learning Lab, they also train graduate students and postdocs to develop their own courses, become a better university professor. And actually, in one of our upcoming webinars in the WeLEAP program, we will be having a conversation with Dr. Lourdes Alleman. She is an associate director at MIT Teaching Plus Learning Lab. And the topic of the talk is going to be unlocking effective classrooms, where we will be discussing a lot of these issues and how we can enhance the learning experience, both teaching and learning experience, both for educators and students. So yeah, I just wanted to put that out there.
Yeah, it's definitely good to start early and learn about these topics such as inclusivity, and just think about not only the technical detail, but also how you want to deliver and what is the take-home message, like what are the main concepts and the thought process that people should develop through a particular class.
Yeah, and it's also about not just delivering the course content because it's good and I want to do it. It's also about designing a course backwards, like rather than thinking, okay, this is a good topic, I want to teach this. Most of the instructors have to work in a way of what are my learning goals, and then design backward from that. Okay, so that all the course activities align to meet those goals. So yeah, definitely like a lot of learning for both students and educators in that. Okay, so with that, we are like moving towards the end of the interview. I'll ask you how your typical workday looks like, and how do you decompress, because being a new faculty member or even a faculty member in general is a very time consuming and a stressful job. So how do you manage everything?
Yes, so one thing that I like of my job is that I don't think there is so much of a typical work day. I feel every day is a little different in a sense. I mean, there are some components that are that repeat, like for example, when I teach, I know certain times I'm going to teach, then there is office hours, then there is class prep, and that gives a little of a rhythm to the semester. But and there are, of course, some meetings that are fixed, for example, research meetings with collaborators or some with students, with people in the community that I work with in these groups and committees that you mentioned. But other than that, the rest is very much flexible at least at this stage. I'm sure maybe it will become more structured as I start to have more students or more commitments even at a university level. But in general, there are three main components to the faculty job that are research, teaching, and service. And my days are some combinations of aspects of those. So typically I start the day just replying emails, going back to my plan, which I do on a semester basis and also on a weekly basis, just to remember myself every day what I actually need to get done today. Because otherwise there is always other things that come up, but it's good to have a plan, and it's good to always keep in mind what are the things that I should get done, and make sure that at least some of them get crossed off by the end of the day. And then I typically either write, I try to write most days, if not every day. It could be editing a paper, writing an abstract, writing a piece of a proposal. Even if it's a small chunk, I try to do a little bit, because over time it builds up toward a finished product. And then, as I said, there are some time that I dedicate to preparing lectures or grading assignments, which I at least I was lucky to teach a small class, and it seems weird, but I actually sort of liked grading the assignments, because I felt like I could learn a lot about how people were thinking about problems. So I spent probably more time than I should have on that, but I was very interested in learning how different people were approaching the problem. And it's funny how you, even if you give a simple problem, there are many different ways to solve it, and you will see all of them in and more in the solutions. So I actually learned a couple of things from some of the students when I was reading the assignments. And then other things that may come up on a more occasional basis, like for example, reviewing an article, or doing some other serving on a panel, serving on some other activity. Those tend to be less repeated, but every now and then I'm spending some time on those activities as well. And in terms of how to decompress, so something that I do two things that are working relatively well for me. One, I did since always, which is doing sport, because I really like both being outdoors and I'm a swimmer, so I try to swim a number of times per week, every week, unless I'm traveling. And I did that throughout college, master, PhD, postdoc, and now I'm still doing that. And that is something that I'm very proud of, because I never gave that up. No matter how crazy the schedule went, I always did that, because it's something that first it helps me think. So I would also argue it's kind of work related, because I think a lot when I swim, or in general when, for example, I take a walk outdoors. But it's also good because it's something that I do for myself, even if the rest of the day is completely filled up, but I still do that. Or the week is filled, but I can still find time to do that. I still feel like I kept a little bit of time just for me, no matter what. So that is something that it helps me feel good, and it's it's also good for time management in a sense, because if you have a commitment that you don't want to give up, then you have to become efficient with everything else. So it helped me in that sense as well. And I mean, I mentioned sports because it's something that I do, but it can be anything really. Something that I told my first PhD student was to pick a hobby, whatever that is that you like, and still keep time for that, no matter what happens, because it's not that extra time, that extra hour of work that is going to make a difference in your work, but it's going to make a difference for your mental health and just your happiness. So it will not destroy your productivity if you keep a few hours every week to do something that you do for yourself. It will make you more accomplished and happier. And then I think it's also important to have a plan, a list of goals that you want to achieve over a certain period of time, and the plan will change over time. Bunch of things will not get done, but some will. And when you look back at your plan on a weekly basis or a semester basis, and you see, I planned to submit, I don't know, one paper, and I wrote 3/4 of a paper, which is not the whole paper, but you still wrote something that didn't existed when you made the plan. So that also helps decompress in a sense, because you always feel like there is more to do. It's important to quantify what you have done over a certain period of time, because at least you can feel you're making progress, and it's not working a lot for no outcome at all.
Mm-hmm. Yeah, thank you so much for sharing that. Definitely being a professor is a hard job, but you can manage it. I mean, it gives hope to, hear your experience, and it gives hope to our audience, hopefully, that you can manage this. Like, you have to prioritize and live a balanced life, and just like break your big goals into small chunks and achieve them on a regular basis. So it's doable. So thank you for being an example of that. So one question I have is, because you came from Italy and you did your PhD there, and now you are successful here in US, and of course there is a lot of advice already available for people who have done PhD here, but I would like to get your opinion on like how your experience was to apply in the PhD program in Italy. What is the typical process? And then how did you like use that opportunity to leap from Italy to US?
Yes, so I was fortunate that my PhD program had a study abroad kind of component. So it was, it didn't actually need to be abroad. It was supposed to be a period that a PhD student would spend at another institution. It didn't need to be the US or Europe. It could have been another university in Italy, but for me it made sense to go to Michigan because I was working on aeroelasticity, and there is a very strong aeroelasticity group there. So that is something that definitely helped me later, because I started building some connections, and even though I didn't study in the US, I did get a US experience during my PhD, which helped just getting to know how the program works, how the system works, even just how people name different things. Like, for example, when I arrived in the US at the beginning, I was very confused. What is a GRA? Like, what is a graduate student assistant? Is this a PhD student, a master student? Can be both? I was very confused because typically in Italy, people, I mean, there are research opportunities at the master level, maybe a little less at the undergraduate level, but most of them are done either as a master thesis or as a master like kind of research experience that is not necessarily associated with a GRA, in the sense the US sees the GRA position. And also the application process is, I mean, I'm sure the application process is different. If you pick different countries, it's different everywhere. So it was also good for me to see that as a PhD student, and definitely helped me during the postdoc, just to get some experience in a different system. And I think in general, I mean, it's important to learn to be flexible and be adaptable, and also learn to search for opportunities to experience a different environment. It doesn't need to be long. It can just be a short period of time, but that helps because then if you have to move again or you have to go to a different system, you already have some data that you made it once and it was good, and it takes time, but in the end you can learn like you learn everything. It's not like there's plenty of people who have a degree outside of the US and are professors in the US. There's plenty of people who have a degree in the US and are professors somewhere else, and all kinds of combinations. So I think it can happen. It's important to not feel like you are behind or you don't know things. You just come from a different background, and maybe you can bring something new from that background that is what makes you valuable in a new environment. So I think it's I don't have a specific advice, but getting exposure to different systems, it's good. You can learn what is good of your background, what maybe can be improved, and you can bring something new in the community. So I would see that as an maybe not an advantage, but a plus that you bring. You come from somewhere else. You are not of the same background. So it can be a difficulty, especially if there are international restrictions or these kind of things, or fewer opportunities for, I don't know, fellowships and all sorts of things. But it's also an advantage in the sense that you have something that other people don't have because they don't have the same background. So that is something that it's a strength in a sense.
Yeah, okay. And one thing I wanted to ask, which in the WeLEAP program we receive a lot of questions, and one of the main questions is about what do professors look into PhD students before hiring. So now you being a student and now being a professor, so you have seen the both sides. So would you recommend any 3-4 major qualities which you look for in your students, or in general like professors look for?
So I still don't have a lot of experience looking at PhD applications, for example, or talking to potential PhD students from a faculty perspective. But something that I would recommend is truly look for people that do something that you're interested in. Make it very clear that you're interested in those topics, because it's never nice to get an email that looks like it was copy pasted from a template, and maybe the person says, I'm very interested in your expertise or your field of research, and they don't even mention what the field of research is. So those are things that, I mean, there is always a time constraint, so there is only as much time one can tailor an email or can take the time to read in deep into a research website or a profile. But I think it's good to be honest. It's good to say what you know about a field, what you don't know about a field, why you're interested, and then ask for some time to talk. And maybe the people respond, maybe the people doesn't respond. If they don't respond, there can be a variety of reasons. Or if they respond no, there can be a variety of reasons. It's not necessarily because maybe they didn't like the person, or they don't want to take a new person. Maybe they are going out on a leave for a year, or maybe they have too many people already, or maybe they don't know if they have funding for a new person, or maybe they have funding but a person wants to do something that is completely different. There are many reasons why it may not work out. But I think it's like all things, it gets better with practice. So I would recommend if you're interested in a field and in a person or a group or a few people, don't feel shy, try. Be aware that the answer can be a no, but not take a no personally. Just move on and try further. And I think in general, my general advice for this kind of interactions is to be yourself, because if you're fake, it will show up at some point, and it will not be fun, because maybe you land a lab where you don't really fit in, or you land a topic that you're not really interested in. But if you are yourself, maybe you're not successful right away, but you will be successful in the end, at some point, after some feedback, after some trials.
Yeah, that's really a great piece of advice. Being yourself is the key. Like sooner or later you will succeed, but you have to stay authentic to yourself.
And be patient.
Yeah. Thank you so much. We learned so much today. Like you discussed a lot about your early career, your current career, and like so many different tips and suggestions. I'm sure the audience listening to this will learn a lot from today's discussion. Do you have any parting words for the audience joining us and aspiring for long-term academic career?
Yeah, so I'll give three. One is don't wait to overcome fears before doing the things that you want to try and want to do, because you overcome fears by doing them. It doesn't happen necessarily before. So if you wait for fear to disappear, you may not, at least if you are like me, probably fear will never disappear. You just learn to ignore that and do things anyway. And eventually you build the confidence to know that even if you are may feel uncomfortable or may feel intimidated, that you will do good, and you go and do things anyway. Then don't aim for perfections, because it's excellence is a thing, perfection is a different thing. So try to excel in what you do, but perfection is something that is not achievable, and if it's achievable, it comes with a very high price in terms of effort and mental effort and struggles that one may place themselves unnecessarily through, just to be perfect and to be as good enough. In some cases is good enough. So I would recommend to be good, try to do the best job, best work that you can do, but also be happy if there are some small imperfections that are just normal to be there. And finally, ask as many people as you can for advice, but then also learn that you have what probably works for you is different from what has worked for other people. So don't feel like you have to follow all of the advice, and especially sometimes you get contrasting advice. It's good to ask, it's good to listen and to take it seriously, but then you also have to be to find your own mix, which means ignoring some of the advice that you received, because you mix the advice in the way that works best for you.
Wow, yeah, that's so true. Thank you so much for sharing that. So yeah, I mean, I really appreciate that you joined us today and shared so much in depth about your life and career path. And it's been amazing to hear your story. And I really appreciate you joining from Italy, being on a different time zone and staying up until this late to have this conversation. Thank you again so much, and we wish you a lot, best of luck. Thank you.
Thank you for the invitation and for organizing this series. This is great. It's amazing. Thank you.
Thank you.